Welcome back. Tonight, we settle in with the story of Cecilia Payne-Gaposchkin, a young astronomer who, in 1925, gazed at the spectra of distant stars and discovered something that would take the scientific establishment 4 years to accept, that the Sun, and indeed all the stars scattered across the night sky, were composed almost entirely of hydrogen and helium, a finding so quietly revolutionary that it reshaped our understanding of the cosmos itself, one gentle observation at a time. Before we begin, take a moment to like the video and subscribe, but only if these stories help you drift off peacefully. Now, dim the lights, pull the blanket a little closer, and together, let us ease gently into tonight's story. Cecilia Payne was born on the 10th of May in the year 1900, in the small town of Wendover, which lies nestled in the Chiltern Hills of Buckinghamshire, England. The town itself was a quiet place, a settlement that had existed for many centuries, with chalk streams running through the surrounding countryside and beech woods covering the nearby slopes. It was the sort of place where the nights were genuinely dark, where the stars could be seen with a clarity that has since become rare in our modern world of electric lights and glowing cities. The house where she was born was a comfortable family home, and into this home she arrived as the second child of Edward John Payne and Emma Leonora Helena Pertz, joining her older brother Humphrey, who had been born 2 years earlier, in 1898. Her father, Edward John Payne, was a man of considerable intellectual accomplishment, though perhaps not of considerable fortune. He worked as a barrister in London, travelling to the city for his legal practice, but his interests extended far beyond the confines of courtrooms and legal briefs. He was a historian of genuine note, having written scholarly works on the history of the New World and the European colonization of the Americas, subjects that required years of patient research and careful thought. He was also an accomplished musician, a man who found solace and joy in the playing of instruments and the study of musical theory, and it seems likely that the household in Wendover was one where books and music were present in abundance, where intellectual pursuits were valued and encouraged, even if wealth was not especially plentiful. Edward was the sort of person who believed in the life of the mind, in the importance of learning and understanding, and though Cecilia would have very few years to know him directly, his influence would linger in the family like the faint scent of old books in a library. Her mother, Emma Leonora Helena Pertz, came from a family with its own distinguished intellectual heritage. She was of Prussian descent, her family having roots in the German-speaking lands of Central Europe, and she was descended from the historian Georg Heinrich Pertz, who had been a significant figure in 19th-century German scholarship. Georg Heinrich Pertz had devoted much of his life to the editing and publication of medieval historical documents, working on the great compilation known as the Monumenta Germaniae Historica, a vast project that sought to preserve and make available the written records of medieval Europe. It was painstaking work, the sort of scholarship that requires decades of patient attention to crumbling manuscripts and faded ink, and Emma carried this heritage with her, this connection to a tradition of learning and careful study. She was a woman who understood the value of education, though she would later struggle with questions about whether such education should be extended equally to her daughters as to her son, a tension that would shape Cecilia's early years in ways both subtle and significant. In 1902, when Cecilia was not yet 4 years old, a sister arrived in the household. This was Leonard, the youngest of the 3 Payne children, and for a brief time the family was complete, a mother and father with 3 young children in their home in the Chiltern Hills. But this completeness was not to last, for Edward John Payne's health was failing, and sometime around 1904, when Cecilia was only 4 years of age, her father died. The details of his illness and passing have faded into the quietness of family history, but the consequences were immediate and lasting. The household lost not only a beloved father and husband, but also its primary source of income, and Emma was left to raise 3 young children largely on her own, with resources that were now considerably diminished. The family circumstances after Edward's death were modest, perhaps more modest than they had been before. Emma had to manage carefully, to make decisions about where money could be spent and where it could not, to consider the futures of her 3 children with a practical eye that was sometimes at odds with her own intellectual heritage and values. There would be no great fortune to smooth the path for Humphrey, Cecilia, and Leonard. no comfortable inheritance to ensure that doors would open easily before them. Instead, there would be careful economy, thoughtful choices, and a reliance on the children's own abilities and determination to make their way in the world. It was not poverty, certainly not the grinding poverty that afflicted so many families in Edwardian England, but it was a life of limits and considerations, a life where opportunities had to be weighed against costs, where the education of children was an investment that had to be justified and planned. And yet, even in these early years of childhood, something was already stirring in young Cecilia, some spark of curiosity that would eventually grow into a lifelong flame of scientific inquiry. When she was approximately 5 years old, she witnessed a meteor streaking across the night sky. It was the sort of event that most children might forget within a day or two, a bright flash of light that comes and goes in an instant, but for Cecilia it was something more. The meteor burned itself into her memory, this visitor from the vastness of space, this piece of cosmic debris that had traveled unimaginable distances only to end its journey in a blaze of light above the English countryside. She wanted to know what it was, where it had come from, why it had appeared and then vanished so quickly. The questions that the meteor raised in her young mind did not fade with time but instead took root, becoming the first seeds of what would eventually become a profound and transformative interest in the workings of the universe. It is worth pausing here to consider what it meant for a young girl in the early 1900s to develop an interest in astronomy. The field was dominated almost entirely by men, and the path from childhood curiosity to professional scientific work was strewn with obstacles that would have seemed insurmountable to most. Women were not expected to become scientists, were not encouraged to pursue such interests beyond the level of amateur enthusiasm, and the universities and observatories where serious astronomical work was conducted were largely closed to them. None of this, of course, would have been apparent to a 5-year-old girl watching a meteor cross the sky, but the world she inhabited was one where her future choices would be constrained in ways that her brother Humphrey would never experience. The path ahead was narrow and uncertain, though she could not yet have known it. Her early education took place at home and at local schools, in the manner that was common for children of her social class in that era. She learned to read and write, studied arithmetic and history, and began her acquaintance with the classical languages that were still considered essential to a proper education. It was during these early years that her remarkable memory first became apparent, a capacity for retention and recall that set her apart from other children her age. She reportedly memorized Latin declensions with an effortlessly that astonished those who taught her, absorbing the complex patterns of noun endings and verb conjugations as though they were simple nursery rhymes. This was not merely rote memorization, the mechanical repetition of sounds without understanding, but a genuine facility with language and pattern, an ability to see the underlying structures and hold them in her mind with clarity and precision. The same mental gifts that would later allow her to master the intricacies of stellar spectra and atomic physics were already present in the young girl learning her Latin grammar in Wendover. Her mother, Emma, watched her daughter's intellectual development with feelings that were somewhat mixed. On the one hand, she came from a family that valued learning and scholarship, and she could not help but recognize and appreciate Cecilia's obvious gifts. On the other hand, she harbored a certain ambivalence about the education of daughters, about whether it was wise or practical to invest heavily in the schooling of girls who would, according to the expectations of the time, eventually marry and devote themselves to domestic life. What was the point, Emma might have wondered, of spending scarce family resources on advanced education for a daughter when that education might never be put to professional use, when the doors that education might open were likely to remain closed anyway? This ambivalence would manifest itself in various ways over the years, sometimes as reluctance, sometimes as outright resistance to Cecilia's educational ambitions, though it never quite succeeded in extinguishing the flame that had been lit in her daughter's mind. Alongside her academic studies, young Cecilia developed an early and abiding interest in the natural world, particularly in the study of plants. She began collecting botanical specimens, gathering flowers and leaves and pressing them carefully, learning to identify different species and to understand the systems by which they were classified. This was not mere idle collecting, the random accumulation of pretty objects, but a systematic and methodical approach to understanding the plant kingdom. She learned the Latin names of the plants she collected, adding to her growing facility with the classical language while simultaneously developing her skills of observation and classification. The same impulse that would later drive her to catalogue and analyze the spectra of thousands of stars was already present in the young girl carefully labeling her pressed flowers with their proper scientific names. There is something deeply characteristic in this early botanical interest, something that reveals the essential nature of the mind that would later revolutionize our understanding of stellar composition. The study of botany in that era was fundamentally a study of classification and pattern, of learning to see the underlying order in the apparent chaos of the natural world. Each plant had its proper place in the great taxonomic system, its genus and species, its family and order, and learning to identify plants meant learning to see the features that mattered, the shapes of leaves and arrangements of petals, the structures of seeds and patterns of growth that distinguished one species from another. It was training in careful observation, in the patient accumulation of data, in the recognition of meaningful patterns, and all of these skills would prove essential in the work that Cecilia would eventually undertake. At some point during these early years, the family made the decision to move from Wendover to London. The reasons for this move were primarily educational, a recognition that the opportunities available in a small country town were limited compared to those that could be found in the great metropolis. London offered better schools, more resources, greater possibilities for children who showed intellectual promise. For Emma, struggling to provide for her 3 children on limited means, the move represented a significant investment in their futures, a gamble that the opportunities of the city would outweigh its costs and difficulties. For young Cecilia, the move meant leaving behind the dark skies of the Chiltern Hills for the gaslit streets of the capital, though her fascination with the heavens would not diminish despite the obscuring glow of city lights. The London to which the Payne family relocated was still the London of the Edwardian era, a vast and complex city that served as the heart of a global empire. It was a city of contrasts, of wealth and poverty existing side by side, of ancient traditions and modern innovations, of horse-drawn carriages sharing the streets with the first motor cars. For a curious child with a keen mind and an expanding range of interests, it offered libraries and museums, lectures and exhibitions, a wealth of intellectual stimulation that would have been impossible to find in Wendover. The move was difficult, as such moves always are, but it opened doors that would prove essential to Cecilia's future development. And so the first 12 years of Cecilia Payne's life drew to a close, years that had seen her born into a comfortable family, orphaned of her father at a tender age, introduced to the wonders of the night sky by a passing meteor, and moved from the countryside to the city in search of better opportunities. She had revealed herself to be a child of exceptional memory and intellectual curiosity, with interests ranging from Latin grammar to botanical classification to the mysterious lights that crossed the heavens. She had a mother who both appreciated her gifts and doubted the wisdom of cultivating them, a brother and sister with whom she shared the modest circumstances of a fatherless household, and a future that was still entirely unwritten. The next years would bring her formal education, further challenges, and the gradual crystallization of her interests into a single consuming passion. But for now, in these quiet years of childhood, the foundations were being laid, slowly and surely, for everything that was to come. In the autumn of 1912, a young Cecilia Payne arrived at the gates of St. Paul's Girls' School in the district of Brook Green, in the west of London, carrying with her the quiet intensity that had already begun to define her character, and perhaps not yet knowing that this institution would serve as the ground in which her scientific ambitions would first take genuine root. She was 12 years old, recently bereaved of her father, and she came from the countryside of Buckinghamshire with an education that had been somewhat irregular, shaped as it was by governesses and her mother's careful attention, and by her own remarkable capacity for absorbing knowledge from whatever books she could find. The school she now entered was not an ordinary establishment for girls, but rather one that had earned a reputation for progressive thinking and genuine intellectual rigor, a place where young women were encouraged to develop their minds with the same seriousness that society typically reserved for their brothers. St. Paul's Girls' School had been founded in 1804, though it had moved to its present buildings in Brook Green only in 1904, and by the time young Cecilia walked through its doors, the institution had become something of a beacon for families who believed that daughters deserved the same quality of education as sons. The High Mistress during Cecilia's years at the school was Frances Ralph Gray, a woman of considerable intellect and administrative capability, who had herself studied at Girton College, Cambridge, and who understood from personal experience both the value of rigorous academic training for women and the obstacles that society placed in their path. Under her leadership, the school maintained high standards across all subjects, and the atmosphere was one of serious purpose combined with genuine care for the development of each student's individual capabilities and interests. The school buildings themselves were designed by the architect Gerald Horsley, and they possessed a certain graceful solidity, with large windows that allowed natural light to flood the classrooms and corridors, and with spaces that seemed to invite contemplation and study. There was a notable hall where assemblies were held and where, on certain occasions, musical performances took place, and this brings us to another figure who moved through those corridors during Cecilia's time there, a man whose presence added an unusual dimension to the school's cultural life. Gustav Holst, the composer who would later become famous for works such as The Planets, served as the director of music at St. Paul's Girls' School beginning in 1905, and he continued in this role throughout the years of Cecilia's attendance and well beyond. He was a gentle and dedicated teacher, known for his ability to inspire genuine love of music in his students, and he composed several pieces specifically for the school and its musical ensembles, including the St. Paul Suite, which he completed in 1913. While Cecilia would not pursue music as a vocation, she was exposed during these formative years to the presence of creative genius at work, to the example of someone who dedicated themselves wholly to understanding and expressing something profound about the nature of the world and human experience. The connection between music and mathematics, between the harmonies of sound and the underlying patterns that govern physical phenomena, is one that many scientists have felt deeply, and perhaps some trace of this awareness began to form in her mind during those years when Holst's compositions filled the school hall, even if she could not yet articulate the relationship between artistic and scientific ways of knowing. When Cecilia first arrived at St. Paul's, her interests were oriented primarily toward the natural world in its most immediate and observable forms, which is to say that she was passionate about botany, about the classification and study of plants, about the intricate structures of leaves and flowers and the systems by which living things were organized into families and genera and species. This was not an unusual interest for a young person who had spent much of her childhood in the English countryside, surrounded by gardens and fields and woodlands, and who possessed the sort of patient, observational temperament that delights in noticing small differences and recording careful details. She had already developed the habit of close attention to the natural world, and botany seemed to offer a framework for organizing her observations into something like systematic knowledge. But at St. Paul's, Cecilia encountered science teaching of a quality and depth that she had not previously experienced, and gradually her interests began to shift toward the physical sciences, toward the underlying principles that govern not only living things but all matter and energy in the universe. This transformation did not happen all at once, but rather unfolded over the course of several years, as she was exposed to new ideas and new ways of thinking about the natural world. The science instruction at St. Paul's was notably strong for a girls' school of that era, though it still fell short of what was available to boys at the leading public schools, and this disparity would eventually become a source of frustration for Cecilia. But in the meantime, she absorbed what was offered with tremendous enthusiasm and supplemented it with her own voracious reading. Among the teachers who influenced her during these years, one name stands out with particular significance, and that is Dorothy Dalgleish, who taught science at St. Paul's and who recognized in young Cecilia a mind of unusual quality. Miss Dalgleish possessed the gift that the best teachers have, which is the ability to see beyond the surface of a student's performance to the potential that lies beneath, and to nurture that potential with appropriate challenges and encouragement. She helped Cecilia understand that science was not merely a collection of facts to be memorized, but a method of inquiry, a way of asking questions about the world and seeking answers through careful observation and logical reasoning. This understanding would prove essential to Cecilia's later work, for she would never be content simply to accept what others had concluded, but would always want to examine the evidence for herself and follow the logic wherever it led, even when it led to conclusions that contradicted established authority. The years of Cecilia's attendance at St. Paul's coincided almost exactly with the period of the First World War, which broke out in the summer of 1914, when she was 14 years old, and which did not conclude until November of 1918, when she was preparing for her final examinations. The war cast its shadow over everything during those years, affecting the school in both obvious and subtle ways. Some of the male teachers left to serve in the military, and the students were aware of brothers and fathers and uncles who were fighting in France and Belgium, and of the terrible casualty lists that appeared in the newspapers with numbing regularity. There were shortages of various supplies, and the general atmosphere was one of anxiety and grief held at bay by routine and duty. For an adolescent girl trying to make sense of the world and her place in it, this context of loss and upheaval must have added a certain urgency to the search for meaning and purpose, though Cecilia rarely spoke in later years about how the war had affected her emotionally. What is clear is that she threw herself into her studies with tremendous intensity, and that she developed during these years reading habits that could only be described as voracious. She did not limit herself to what was assigned in her classes, but sought out scientific texts independently, reading far beyond her level and struggling to understand concepts that were not being taught to her directly. She had access to the school library, of course, but she also found ways to obtain books from other sources, and she read widely in physics and chemistry and astronomy, building up a knowledge base that was remarkable for someone of her age and circumstances. This self-directed learning was driven not by any external requirement or reward, but by genuine intellectual hunger, by a deep need to understand how the world worked at its most fundamental level. It was during this period of independent reading that Cecilia first encountered astronomical concepts in any serious way, moving beyond the simple facts about planets and stars that any educated person might know, and beginning to grapple with questions about the nature of celestial bodies and the methods by which astronomers studied them. She read about spectroscopy, the technique of analyzing light to determine the composition of distant objects, and though she could not yet fully understand the physics involved, she was captivated by the idea that it was possible to learn what the stars were made of without ever leaving the Earth, simply by examining the light that traveled across the vast emptiness of space to reach our eyes and our instruments. This was a seed planted in fertile ground, and though it would not flower fully until her years at Cambridge, it was already taking root in her mind during her final years at St. Paul's. As Cecilia progressed through the school, her frustration with the limited science offerings available to girls grew more acute. She was aware that boys at schools like Eton and Harrow and Winchester had access to laboratories and equipment and specialized instruction that was simply not available to her, and she resented this inequality with increasing sharpness. The disparity was not a matter of any fault in St. Paul's itself, which was doing as much as any girls' school of the time, but rather a reflection of broader social attitudes about what subjects were appropriate and necessary for young women to study. The prevailing assumption was that girls might benefit from some general scientific knowledge, enough to make them interesting conversationalists and intelligent mothers, but that they did not need the deep technical training that would prepare them for careers in scientific research. Cecilia knew that this assumption was wrong, and she was determined to find a way around the barriers it created. Her family, meanwhile, had expectations of their own about the direction her education should take, and these expectations pulled her toward the classics rather than the sciences. Her mother, who had made considerable sacrifices to provide her children with good educations, naturally hoped that Cecilia would pursue a respectable academic path, and in the early 20th century, the most prestigious academic path for a woman was through the study of classical languages and literature. A woman who excelled in Greek and Latin might hope for a position teaching at a good school, or for the kind of general intellectual respect that came from mastery of the ancient world. A woman who wished to pursue physics or astronomy was entering territory that was far less charted and far less socially acceptable. There must have been conversations, though we do not have detailed records of them, in which Cecilia made clear her preference for the natural sciences and in which her family expressed concerns or reservations about this choice. In the end, Cecilia prevailed, as she would prevail in so many struggles throughout her life, through a combination of determination, ability, and the sheer force of her conviction that she was meant for scientific work. She prepared for the Cambridge entrance examinations with characteristic thoroughness, studying not only the subjects in which she would be tested but also material that lay beyond the examination requirements, because she wanted to understand as much as she possibly could, not merely to pass a test. Her preparation was aided by a scholarship she had won through rigorous examination earlier in her school career, which had helped to ease the financial burden on her family and had confirmed, if confirmation were needed, that she possessed academic abilities of an unusual order. The Cambridge entrance examinations in that era were demanding affairs, designed to identify students who were capable of benefiting from university-level instruction, and they required not only knowledge but the ability to think clearly under pressure and to express oneself with precision and coherence. Cecilia sat for these examinations in 1919, as the world was still recovering from the influenza pandemic that had followed the war, and as society was beginning the slow process of returning to something like normal life. She performed with distinction, earning marks that placed her among the top candidates and securing her admission to Newnham College, one of the two women's colleges at Cambridge, for the following academic year. And so, in the autumn of 1919, Cecilia Payne departed from St. Paul's Girls' School and from London, carrying with her the foundation that 7 years of education had provided, and carrying also the questions that had begun to form in her mind about the nature of the stars and the methods by which their secrets might be uncovered. She was 19 years old, and she was about to enter an environment where those questions would be sharpened and deepened, where she would encounter both inspiring teachers and frustrating limitations, and where she would begin the work that would eventually transform our understanding of the universe. But all of that lay ahead, and for now, in the gentle transition from school to university, she was simply a young woman with unusual gifts and unusual determination, setting out on a path that very few women had walked before her. In the autumn of 1919, a young woman of 19 years arrived at Newnham College, one of the two women's colleges at the University of Cambridge, carrying with her the accumulated hopes and uncertainties that accompany any significant transition in life. Cecilia Payne had won a scholarship to study at this ancient university, and she came with the intention of pursuing the natural sciences, though the precise direction her studies would take remained, at that early moment, somewhat undetermined. Newnham College stood among gardens and quiet pathways, a place where women could pursue academic work in an environment that was, by the standards of the time, relatively progressive, though the women who studied there existed in a kind of academic limbo, permitted to attend lectures and sit examinations but denied the full recognition that their male counterparts received as a matter of course. The buildings of Newnham were built of red brick, arranged around lawns and courtyards, and the atmosphere there combined scholarly seriousness with a certain domestic comfort, as the college attempted to create a space where women might develop their intellectual abilities without entirely overturning the conventions of the age. Cecilia had initially enrolled to study botany, physics, and chemistry, a combination of subjects that reflected her broad curiosity about the natural world and the ways in which systematic observation and careful reasoning might reveal the underlying principles that govern material phenomena. Botany appealed to her love of classification and detailed examination. Physics offered the promise of fundamental laws expressed in mathematical terms, and chemistry provided a bridge between the abstract and the tangible, showing how matter transforms and combines according to predictable rules. These early studies laid important groundwork, teaching her laboratory techniques and mathematical methods, introducing her to the habits of careful measurement and precise recording that would serve her throughout her scientific career. She attended lectures in drafty halls, took notes in the careful handwriting of the period, and began to find her way among the libraries and laboratories of Cambridge, learning the rhythms of academic life and discovering which subjects quickened her interest and which left her attention wandering. The pivotal moment came in the form of a lecture, delivered by the astronomer Arthur Stanley Eddington, who had recently returned from an expedition that would alter the course of modern physics. In May of 1919, just months before Cecilia arrived at Cambridge, Eddington had led an expedition to the island of Principe, off the west coast of Africa, to observe a total solar eclipse, and a parallel expedition had travelled to Sobral in Brazil. The purpose of these expeditions was to test a prediction made by Albert Einstein's general theory of relativity, which proposed that massive objects such as the Sun would bend the path of light passing near them, causing the apparent positions of stars to shift slightly when observed close to the Sun's edge during an eclipse. Eddington's measurements, and those of his colleagues, confirmed Einstein's prediction, providing dramatic observational support for a theory that reimagined gravity not as a force acting at a distance but as a curvature in the fabric of spacetime itself. The announcement of these results had caused considerable excitement in the scientific world and beyond, and Eddington, who possessed a gift for clear exposition, gave a lecture at Cambridge describing the expedition, the observations, and their profound implications. Cecilia attended this lecture, and the effect upon her was immediate and lasting. She later recalled that she had been so captivated by what she heard that she had gone home and written down everything Eddington had said, reconstructing his lecture from memory almost word for word, an exercise that speaks both to her remarkable powers of recall and to the intensity of her engagement with the material. Here was a description of an expedition to a remote island, of careful preparations and anxious waits for clear skies, of photographic plates exposed during the brief minutes of totality and then painstakingly measured to determine the positions of stars, and all of this in service of testing a theory about the fundamental nature of space and time. The combination of adventure and precision, of travel to distant places and meticulous analysis in quiet laboratories, of observations made under difficult conditions and conclusions that reach toward the deepest questions about the universe, seems to have crystallized something in her mind. The experience of hearing Eddington speak was, by her own later account, transformative, and she could not afterwards resume her previous studies with the same engagement, for she had glimpsed a field that answered to her deepest intellectual longings. Shortly after attending Eddington's lecture, Cecilia made the decision to abandon her original course of study and to devote herself instead to astronomy. This was not a simple administrative matter, for it required adjustments to her program and negotiations with the college authorities, but she pursued the change with the determination that would characterize her throughout her career. Botany, physics, and chemistry had each offered something of value, but astronomy, she now understood, was the subject that would claim her full attention, the discipline where she could combine mathematical reasoning with observational work, where the questions were vast and the methods rigorous, and where, perhaps, she might make some contribution to human knowledge about the cosmos in which we all find ourselves. Her studies at Cambridge brought her into contact with several figures who would influence her development as a scientist. Ernest Rutherford, the New Zealand-born physicist who had done foundational work on the structure of the atom and who would later receive the Nobel Prize in Chemistry, gave lectures at Cambridge during this period, and Cecilia attended them, absorbing what she could of the new physics that was transforming the understanding of matter at its most fundamental level. Rutherford was a powerful lecturer and a towering figure in the physics of the day, but he was also notoriously dismissive of women students, making little effort to hide his view that women did not belong in physics laboratories or lecture halls. Cecilia experienced this dismissiveness directly, as did other women who attempted to pursue scientific studies at Cambridge, and while such treatment was dispiriting, it did not deter her from continuing her education, though it surely contributed to her growing awareness that the British scientific establishment was not eager to welcome women into its ranks. The Cavendish Laboratory, where much of the pioneering work in atomic physics was conducted, was a place of great intellectual ferment, and Cecilia attended lectures there, learning about electrons and atomic nuclei, about radioactive decay and the emerging quantum theory, all of which would prove relevant to her later work on the composition of stars. More directly influential on her astronomical education was Edward Arthur Milne, an astrophysicist who taught at Cambridge and who introduced her to the theoretical aspects of stellar astronomy. Milne was interested in the physics of stellar atmospheres, in the ways that the laws governing the behavior of gases and radiation could be applied to understand the conditions in the outer layers of stars, and his teaching opened Cecilia's eyes to the possibilities of combining physics and astronomy in a rigorous mathematical framework. Under his guidance, she began to appreciate that stars were not merely points of light to be catalogued and tracked across the sky, but were physical objects whose properties could be deduced from careful analysis of the light they emitted, and that the same laws of physics that govern terrestrial phenomena also operated in the distant reaches of space. This insight, which seems perhaps obvious in retrospect, was still being established during this period, and Milne was one of those working to place astrophysics on a firm theoretical foundation. Practical observatory work formed another important part of her Cambridge education. She worked at the Cambridge Observatory under the direction of Hugh Frank Newell, who supervised students in the techniques of observational astronomy. The observatory, with its domes and telescopes and the particular quiet that settles over such places during nights of observation, became a familiar environment to her, a place where she learned to operate instruments, to expose photographic plates, to track celestial objects as they moved across the sky, and to process and analyze the resulting data. It was here that she received her introduction to stellar spectroscopy, the technique of spreading the light from a star into its component wavelengths and examining the resulting spectrum for the dark lines that indicate the presence of particular chemical elements. Each element absorbs light at characteristic wavelengths, leaving its signature in the spectrum, and by studying these spectral lines astronomers could begin to determine what stars were made of, a question that had seemed almost impossibly remote only a few decades earlier. This technique of spectral analysis would become central to Cecilia's later research, and the practical experience she gained at the Cambridge Observatory laid the groundwork for the work that would make her scientific reputation. Throughout her time at Cambridge, Cecilia was aware, as all women students there were aware, of the peculiar limitation under which they labored. The University of Cambridge did not award degrees to women during this period, a policy that would not change until 1948, nearly 3 decades after Cecilia completed her studies. Women could attend lectures, provided the individual lecturers permitted it, and they could sit the examinations, and they could receive results that indicated how they would have been classified had they been men, but they could not receive the actual degrees that represented the formal recognition of their academic achievement. When Cecilia completed her studies at Cambridge, she received only a nominal certificate, a piece of paper acknowledging that she had done the work but withholding the degree that would have been granted automatically to any man with the same record. This situation was frustrating and unjust, and it underscored the larger reality that British astronomy, and British science more broadly, offered very limited prospects for women who wished to pursue research careers. The positions available, the fellowships and lectureships and observatory posts, went almost exclusively to men, and a woman who wished to devote her life to scientific research would find few opportunities in Britain regardless of her abilities. During her Cambridge years, Cecilia met Leslie John Comrie, a New Zealand-born astronomer who worked on computational methods in astronomy and who would later make important contributions to the mechanization of scientific calculation. Comrie recognized her abilities and, understanding the limitations she faced in Britain, encouraged her to consider pursuing her career in the United States, where the situation for women in astronomy, while far from ideal, was somewhat more promising than in England. American observatories, particularly the Harvard College Observatory, had a history of employing women in certain roles, and while these positions were often poorly paid and carried limited status, they at least represented opportunities for substantive research work that simply did not exist for women in Britain. Comrie's encouragement planted a seed that would eventually bear fruit in Cecilia's decision to cross the Atlantic in search of a scientific career. The years at Cambridge, from 1919 to 1923, were thus a period of formation, during which Cecilia Payne discovered her vocation and began to develop the skills and knowledge that would enable her to pursue it. She had arrived as a scholarship student with broad interests in the natural sciences and had departed, or rather was preparing to depart, as a young astronomer with a solid grounding in physics and mathematics, practical experience in spectroscopic observation, and a growing understanding that if she wished to make a career in her chosen field, she would need to seek opportunities beyond the shores of Britain. The lectures she had attended, the laboratories where she had worked, the observatory nights spent examining the light of distant stars, and the conversations with mentors and fellow students had all contributed to shaping her into a scientist, though much of her most important work still lay ahead, waiting to be accomplished in a new country and a new setting. The nominal certificate she received in lieu of a degree was a reminder of the obstacles that remained, but it did not diminish what she had learned or the determination she carried with her as she contemplated the next stage of her journey. In the late summer of 1923, a young woman from Wendover in Buckinghamshire prepared to leave behind everything she had known, the gentle English countryside and the ancient stone buildings of Cambridge University and the particular quality of light that falls across the fens in autumn, all of it soon to be exchanged for something quite unknown and rather far away. Cecilia Payne was 23 years old, and she had secured passage on a steamship bound for America, where a position awaited her at the Harvard College Observatory in Massachusetts. The journey itself would take approximately 10 days, depending on weather conditions in the North Atlantic, and during those days she would have ample time to consider the magnitude of what she was undertaking. which was nothing less than the complete transformation of her professional and personal circumstances in pursuit of a science that the universities of her homeland would not permit her to study in any formal capacity. The opportunity had come about through the efforts of Harlow Shapley, who had become director of the Harvard College Observatory just 2 years prior, in 1921, and who held views about the participation of women in astronomical research that were, for his era, notably progressive. Shapley had inherited an institution with a long and rather unusual history of employing women in scientific work, a tradition that stretched back to the 1880s when Edward Charles Pickering had first begun hiring women to perform the painstaking labor of examining and classifying stellar spectra captured on photographic plates. These women, who came to be known informally as the Harvard computers, had over several decades built up an extraordinary body of knowledge about the stars, and Shapley saw no reason to discontinue this practice. Indeed, he actively sought to expand it, recognizing that capable scientific minds were not distributed according to any particular pattern of gender, and that the observatory stood to benefit from recruiting talented individuals regardless of such considerations. Cecilia had encountered Shapley during one of his visits to England, and she had spoken with him about her desire to pursue graduate work in astronomy, a field in which Cambridge University could offer her no formal degree despite the excellence of its teaching and research. Shapley had been impressed by her knowledge and her obvious passion for the subject, and he had suggested that she apply for a fellowship at Harvard, where such barriers to women's advancement, while certainly not absent, were at least somewhat less insurmountable. The fellowship in question was one that had been established specifically to support women astronomers, a reflection of both the observatory's historical employment of women and a growing, if still limited, recognition that scientific education should be available to those with the aptitude to benefit from it. The award would cover her fees and provide a modest stipend for living expenses, enough to sustain a careful and frugal existence while she pursued her research. And so in September of 1923, Cecilia Payne boarded a steamship at one of the great English ports, carrying with her whatever possessions she deemed essential for her new life and leaving behind her mother, her siblings, and the familiar rhythms of English society. The crossing of the Atlantic by steamship was by this time a well-established form of travel, the great ocean liners having made the journey countless times, and yet there remained something irreducibly significant about placing oneself aboard a vessel and watching the coastline of one's homeland recede into grey distance. The ship would have moved through the English Channel and out into the open Atlantic, where the swells grew larger and the horizon became an unbroken circle of water-meeting sky, and Cecilia would have had many hours to read, to think, and to contemplate the scientific problems that awaited her attention. The voyage across the Atlantic in 1923 was neither particularly dangerous nor particularly comfortable, occupying a middle ground that characterized much ocean travel of the period. The steamships were reliable and the routes well charted, but the accommodation for a young woman traveling on limited funds would have been modest, the cabin small and the meals serviceable rather than elegant. Still, the journey provided a kind of transitional space, a liminal period between one life and the next, during which Cecilia could begin the psychological adjustment that such a significant change requires. She was leaving behind not merely a country but an entire system of expectations about what a woman of her background and education might reasonably hope to achieve, and she was sailing toward a place where, if the barriers were not entirely removed, they were at least configured somewhat differently. Upon arriving in the United States and making her way to Cambridge, Massachusetts, Cecilia Payne would have encountered a landscape and a culture quite different from what she had known. The town of Cambridge sits just across the Charles River from Boston, and in 1923 it was already home to two of America's most prestigious universities, Harvard and the Massachusetts Institute of Technology, giving the area a distinctly academic character that might have felt somewhat familiar even as its details were strange. The architecture was different from the ancient colleges of Cambridge in England. The accents of the people were different, the food was different, and the social customs were different in ways both large and small. This initial period of adjustment, what we might now call culture shock, was something that Cecilia would have to navigate while simultaneously beginning her scientific work, a dual challenge that required considerable reserves of adaptability and determination. The Harvard College Observatory was located on Garden Street, a pleasant thoroughfare in the northern part of Cambridge, and when Cecilia first approached it, she would have seen a complex of buildings dominated by the great dome that housed the historic 15-inch refractor telescope. This instrument had been installed in 1847, making it one of the oldest large telescopes in America, and while it was no longer at the cutting edge of observational astronomy, it remained a working scientific instrument and a symbol of the observatory's long history. The dome itself was a substantial structure, painted white and mounted on a cylindrical base, and it could be rotated to allow the telescope to be pointed at different portions of the sky. Cecilia would come to know this building well, though her own work would be conducted not at the eyepiece of a telescope, but rather in the rooms where the observatory's vast collection of photographic plates was stored and studied. And it was this collection of plates that constituted the true treasure of the Harvard College Observatory, a resource of almost incomprehensible richness for anyone interested in the study of stellar spectra. Over the preceding decades, beginning in the 1880s under the direction of Edward Charles Pickering, the observatory had systematically photographed the spectra of hundreds of thousands of stars, capturing on glass plates the characteristic patterns of light and dark lines that each star produced when its light was passed through a prism or diffraction grating. By the time Cecilia arrived in 1923, the collection had grown to more than 500,000 individual plates, each one a permanent record of the spectral signature of one or more stars, and together they formed a library of stellar information that was simply unmatched anywhere else in the world. The photographic plates themselves were physical objects of considerable delicacy, consisting of glass rectangles coated with light-sensitive emulsion on which the stellar spectra had been recorded. They required careful handling and storage, and reading them required both good eyesight and extensive training in the interpretation of spectral patterns. The women who had performed this work at Harvard over the years had developed extraordinary expertise, learning to recognize at a glance the subtle differences between one spectral type and another, and their accumulated knowledge was preserved not only in published catalogues but in an oral tradition of instruction passed from experienced classifiers to newcomers. Among these women, the most distinguished was Annie Jump Cannon, who at the time of Cecilia's arrival was 60 years old and had been working at the observatory for more than a quarter of a century. Cannon was a remarkable figure, a woman who had overcome the limitations placed on her gender and had achieved an international reputation as the foremost authority on stellar spectral classification. She was also profoundly deaf, having lost most of her hearing in her early 30s, and she conducted her work and her conversations with the assistance of various accommodations that she and her colleagues had developed over the years. Despite this challenge, or perhaps in some ways because of it, Cannon possessed an extraordinary ability to focus her attention on the patterns of spectral lines, and she had personally classified more stars than any other human being in history. When Cecilia Payne met Annie Jump Cannon, she encountered a mentor whose experience and expertise would prove invaluable in the years ahead. Cannon took an interest in the young Englishwoman, recognizing in her the same passion for stellar science that had animated her own career, and she became both a professional guide and a personal friend. The relationship between them was not without its complexities, as the two women held different views on certain scientific questions and different positions within the observatory's hierarchy, but it was fundamentally one of mutual respect and genuine affection. Cannon would introduce Cecilia to the practical techniques of spectral classification and would share with her the accumulated wisdom of decades spent examining photographic plates, while Cecilia would bring to the work a theoretical sophistication that complemented Cannon's empirical mastery. The work to which Cecilia was immediately introduced was connected to the great project that had defined the observatory's research program for many years, the creation of the Henry Draper Catalogue. This monumental undertaking, named in honor of a wealthy amateur astronomer whose widow had funded much of the work, aimed to classify the spectra of every star visible from the northern hemisphere down to a certain limiting brightness, and eventually to extend this classification to fainter stars and to the southern skies as well. The catalogue used a system of spectral types that Cannon herself had refined and systematized, arranging stars into categories designated by letters of the alphabet according to the patterns of absorption lines visible in their spectra. The sequence of letters, which went O, B, A, F, G, K, M, with various subdivisions and extensions, represented what was understood to be a progression of stellar temperatures, though the full physical interpretation of this sequence was not yet complete. Cecilia threw herself into this work with characteristic intensity, learning the techniques of spectral classification from Cannon and the other women computers while also pursuing her own theoretical investigations into the physical meaning of the spectral patterns. Her days were spent examining photographic plates, peering through magnifying glasses at the tiny images of stellar spectra and noting the presence or absence of particular spectral lines, and her evenings and nights were often devoted to reading and thinking about the theoretical physics that might explain what she was observing. The pace of work was demanding, but Cecilia found it exhilarating rather than exhausting, for she was at last engaged in the scientific research that she had longed to pursue. Her living conditions during this period were modest in the extreme, reflecting both the limited funds available through her fellowship and her own lack of concern for material comfort. She rented inexpensive rooms in Cambridge, furnishing them with only the most essential items and devoting most of her stipend to books and other necessities for her work. The fellowship that supported her, the Edward C. Pickering Fellowship, had been established to honor the memory of the previous observatory director, and it provided just enough money for a careful person to survive while pursuing research. Cecilia was such a person, having learned frugality during her years in England, and she managed her finances with the same methodical attention that she brought to her scientific work. The adjustment to American academic life presented its own set of challenges, some of them minor and some more substantial. The customs of American universities were different from those of Cambridge, the relationships between students and faculty were configured differently, and the expectations regarding women's participation in academic life were simultaneously more progressive in some respects and more restrictive in others. Cecilia had to learn when to speak and when to remain silent, how to navigate the social hierarchies of the observatory, and how to present herself in a way that would be taken seriously by her male colleagues without violating the unwritten rules that governed women's behavior in professional settings. Through all of this, she was sustained by the work itself, by the daily immersion in the patterns of stellar spectra and the gradually forming conviction that she was approaching something important, some insight into the nature of the stars that had not yet been fully articulated. The 500,000 photographic plates in the observatory's collection were a kind of silent testimony, each one capturing a moment of starlight that had traveled for years or centuries or millennia before falling upon the glass, and Cecilia felt the privilege of being allowed to study them. And so we come now to the years between 1923 and 1925, a period during which Cecilia Payne would undertake the doctoral research that would, in time, come to be recognized as one of the most significant contributions to our understanding of the stars, though at the moment of its completion, its most important conclusion would be questioned and softened, only to be confirmed some years later when independent evidence made the truth of her findings undeniable. When Cecilia arrived at the Harvard College Observatory in the autumn of 1923, she was 23 years old, and she carried with her the knowledge she had gained from her studies at Cambridge, including her attendance at a lecture by Arthur Eddington that had so profoundly shaped her determination to pursue astronomy. She came to America on a fellowship established to support women in scientific research, and she found herself in an environment that was, in many ways, uniquely suited to her particular gifts and interests. The Harvard Observatory possessed an extraordinary collection of photographic plates, hundreds of thousands of images of stellar spectra that had been gathered over decades, and it was here, among these quiet records of starlight, that Cecilia would find the data she needed to pursue the questions that interested her most deeply. Her advisor was Harlow Shapley, who had himself made important contributions to our understanding of the scale of the galaxy and the position of our solar system within it. Shapley recognized in Cecilia a rare combination of mathematical ability, physical intuition, and determined focus, and he encouraged her to pursue a doctoral thesis that would apply recent advances in theoretical physics to the interpretation of stellar spectra. The spectra of stars, those rainbow patterns of light separated into their component wavelengths, had long been studied and classified, but the underlying physical processes that produce the patterns of bright and dark lines were only beginning to be understood in a rigorous way, and it was to this problem that Cecilia turned her attention with considerable energy and care. The key to her approach lay in the work of Meghnad Saha, an Indian physicist who had developed a mathematical equation describing the ionization of atoms at different temperatures. When atoms are heated to very high temperatures, such as those found in the outer layers of stars, some of their electrons are stripped away, leaving the atoms in an ionized state. The degree of ionization depends on the temperature and pressure of the surrounding gas, and Saha had shown how this relationship could be expressed in a precise mathematical form. This equation, known as the Saha ionization equation, provided a tool for interpreting the patterns of spectral lines in terms of the physical conditions in stellar atmospheres, and Cecilia recognized that by applying this equation systematically to the vast collection of stellar spectra available at Harvard, she might be able to determine not only the temperatures of stars but also the relative abundances of different chemical elements in their outer layers. This was painstaking work, requiring careful measurement and calculation, and Cecilia approached it with the methodical thoroughness that would characterize all of her scientific endeavors. She analyzed the spectra of numerous stars, comparing the observed strengths of spectral lines with the predictions of the Saha equation, and gradually she built up a picture of the conditions in stellar atmospheres that was far more detailed and physically grounded than anything that had come before. Her analysis led her to conclusions about the temperatures of different classes of stars, confirming and extending the classification schemes that had been developed by Annie Jump Cannon and others who had worked with the Harvard spectral plates over the preceding years. But it was her findings regarding the chemical composition of stars that proved most surprising and most consequential, though the full recognition of their importance would take some years to emerge. When Cecilia applied the Saha equation to determine the abundances of different elements in stellar atmospheres, she found something that seemed, at first, almost impossible to believe. The spectra indicated that hydrogen was overwhelmingly the most abundant element in the stars she studied, far exceeding the abundance of any other element, and helium, too, appeared to be present in quantities vastly greater than any of the heavier elements. This was a striking result because it contradicted the prevailing assumption that the chemical composition of stars was broadly similar to the chemical composition of the Earth, with iron, silicon, oxygen, and other familiar elements making up the bulk of stellar matter. The idea that stars had Earth-like elemental abundances was not based on careful analysis so much as on a kind of intuitive expectation, a sense that the matter of the universe should be more or less uniform in its composition, and that the familiar materials of our own planet should be representative of cosmic matter generally. Cecilia's data suggested otherwise, pointing to a universe in which hydrogen and helium dominated, with the heavier elements that make up the Earth and its rocks and oceans constituting only a small fraction of the stellar material. This was a revolutionary conclusion, though Cecilia herself seems to have approached it with a mixture of excitement and caution, aware that such a dramatic departure from accepted thinking would require strong evidence and careful argument. She consulted with other astronomers as she worked through her analysis, seeking guidance and perspective on her findings. Among those she corresponded with was Henry Norris Russell, one of the most prominent and respected astronomers of the time, known for his work on stellar evolution and for the diagram that bears his name, which plots the luminosity of stars against their temperatures. Russell had considerable influence in the astronomical community, and his opinion carried great weight. When Cecilia shared her results with him, including her conclusion about the extraordinary abundance of hydrogen in stellar atmospheres, Russell expressed skepticism. He believed that the result was likely spurious, an artifact of some error or oversimplification in the analysis, rather than a true reflection of stellar composition. Russell's doubts were not unreasonable from the perspective of the time, given the novelty of the method Cecilia was using and the surprising nature of her conclusions, but the effect of his skepticism was to persuade Cecilia to soften the presentation of her findings. In her thesis, she noted the apparent high abundance of hydrogen but described the result as almost certainly not real, suggesting that it likely reflected some peculiarity in the behavior of hydrogen atoms that was not yet fully understood, rather than an actual dominance of hydrogen in stellar matter. This was a concession to the prevailing views and to the authority of established astronomers, and it represented a pulling back from the full implications of her own careful work. Her thesis committee included Harlow Shapley, who served as her advisor, as well as Henry Norris Russell and other distinguished figures in the field. The committee evaluated her work and found it to be of exceptional quality, a thorough and rigorous application of physical principles to astronomical observations that advanced the understanding of stellar atmospheres in significant ways. In 1925, Cecilia completed her dissertation, a substantial work of 215 pages titled Stellar Atmospheres, a contribution to the observational study of high temperature in the reversing layers of stars. The title itself conveys something of the careful, technical nature of the work, which was concerned with the behavior of atoms in the hot outer layers of stars, the regions where the light we observe is shaped and filtered before it travels across space to reach our telescopes and spectroscopes. The thesis was published as Harvard Observatory Monograph No. 1, the first in a new series of publications from the Observatory, which perhaps reflected the esteem in which Shapley and others held the work. Cecilia was 25 years old at the time of its completion, and she became the first person, whether male or female, to earn a doctorate in astronomy from Radcliffe College, which was the coordinate institution through which women could receive degrees from Harvard at that time. It was a notable achievement by any measure, though the constraints placed on women in academic life meant that the recognition and opportunities that followed would not be commensurate with the quality of the work she had produced. In the years following the completion of her thesis, the question of stellar composition remained unsettled, but evidence began to accumulate that supported Cecilia's original conclusion about the abundance of hydrogen. Other astronomers, using different methods and different data, arrived at results consistent with hers, and gradually the scientific community came to accept that stars were indeed made primarily of hydrogen and helium, with the heavier elements constituting only a small percentage of stellar matter. By 1929, approximately 4 years after Cecilia had completed her thesis, Henry Norris Russell himself acknowledged that her findings regarding hydrogen were correct. He published work of his own that confirmed the high abundance of hydrogen in the Sun and other stars, and he credited Cecilia with having been the first to reach this conclusion, though the belated nature of this acknowledgement and the fact that Russell's confirmation is sometimes remembered more prominently than Cecilia's original discovery reflect the complexities of credit and recognition in scientific history. The significance of Cecilia's thesis extended beyond the specific findings about hydrogen, important as those findings were. Her work demonstrated the power of applying the methods of physics to astronomical problems, showing that the spectra of stars could be interpreted quantitatively to reveal the physical conditions and chemical compositions of distant objects that could never be visited or sampled directly. This approach, which we might now call astrophysics, was still relatively new in the 1920s, and Cecilia's thesis was an exemplary demonstration of its potential. She showed that the tools of quantum theory and statistical mechanics, developed to describe the behavior of atoms in laboratory conditions, could be extended to the extreme environments of stellar atmospheres, bridging the gap between terrestrial physics and the remote and inaccessible realm of the stars. The astronomer Otto Struve, who was himself a significant figure in 20th century astronomy, later described Cecilia's dissertation as the most brilliant doctoral thesis ever written in astronomy, a judgment that reflects both the originality of her conclusions and the quality of her methods. Such assessments are of course subjective, and the history of science contains many remarkable pieces of work, but Struve's statement captures something of the recognition that eventually came to Cecilia's thesis, even if that recognition was slower and less complete during her own lifetime than it might have been. The story of the thesis and its reception illustrates some of the challenges that Cecilia faced as a woman in a field dominated by men, and as a young researcher whose conclusions challenged the views of more established figures. The pressure to soften her findings about hydrogen, and the years of delay before those findings were fully accepted, remind us that scientific knowledge does not emerge in a simple, linear fashion, but is shaped by social dynamics, by the authority of established figures, and by the courage and persistence required to advance ideas that go against prevailing assumptions. Cecilia possessed that courage and persistence, and though she accepted the suggestion to describe her hydrogen result as probably spurious, she did not abandon her commitment to rigorous observation and careful reasoning, and the truth of her findings eventually became clear. As we consider the quiet years of work that produced this thesis, the long hours spent examining spectral plates and performing calculations, we can appreciate the patience and dedication that scientific research requires. There is a kind of peacefulness in such work, a slow accumulation of evidence and understanding, and Cecilia Payne pursued it with a steadiness and focus that would continue to characterize her career in the decades that followed. Her thesis, completed at the age of 25, marked not an ending but a beginning, the first major contribution in what would be a long and productive life devoted to the study of the stars. And though she could not have known at the time just how influential her work would prove, she had taken her place among those who have advanced our understanding of the universe through careful observation and thoughtful analysis. In the years following her doctoral thesis, Cecilia Payne found herself in a position that was both intellectually exhilarating and professionally peculiar, for she had produced what many would later recognize as the most brilliant doctoral dissertation ever written in the field of astronomy, and yet Harvard College Observatory could not quite determine what to do with her, or rather, could not quite bring itself to grant her the recognition that her work so clearly merited. She remained at the observatory, yes, continuing her research into the nature of stars, but her official title was that of technical assistant to Harlow Shapley, a designation that conveyed little of her actual contributions and carried with it a salary so modest that it barely covered her living expenses in Cambridge, Massachusetts. This arrangement would persist for nearly a decade, from 1925 through 1934, a period during which she published prolifically, trained students, and built an international reputation, all while Harvard kept her name out of its course catalogues and paid her a fraction of what her male colleagues received for far less distinguished work. The position of technical assistant was, in its way, a kind of administrative fiction, a category that allowed the observatory to retain her services without confronting the uncomfortable question of whether a woman might be appointed to the faculty. Harvard had never granted a woman a faculty position in astronomy, and the university showed no particular inclination to begin with Cecilia Payne, regardless of the quality of her research or the originality of her ideas. Shapley valued her work tremendously, and he did what he could within the constraints of the institution to keep her at the observatory, but what he could do was limited by the customs and prejudices of the time, and so she remained a technical assistant, her name appearing on papers and in scholarly correspondence while remaining absent from the official roles of Harvard's teaching staff. It was a liminal existence, neither one thing nor another, and it required of her a particular kind of fortitude, a willingness to continue doing excellent work even when that work went unacknowledged by the very institution that housed her. Her research during these years was characterized by the same meticulous attention to detail that had distinguished her doctoral thesis, and she applied herself to the study of stellar spectra with a persistence that bordered on the monastic. She would arrive at the observatory early in the morning and remain there late into the evening, often working 12-hour days as she analyzed the photographic plates that contained the spectral signatures of thousands upon thousands of stars. Each plate was a record of light that had traveled unimaginable distances across the cosmos, and each spectrum told a story about the temperature and composition and luminosity of the star from which it had originated, and Cecilia Payne read these stories with a fluency that few of her contemporaries could match. The work was painstaking and slow, requiring hours of careful measurement and calculation, but she found in it a kind of meditative satisfaction, a sense that she was gradually assembling a more complete picture of the stellar universe. The papers she published during this period covered a remarkable range of topics within stellar astronomy, from investigations of stellar luminosities to detailed studies of variable stars to comprehensive analyses of the most luminous stars in the galaxy. Variable stars held a particular fascination for her, these objects whose brightness fluctuates over time in patterns that can reveal fundamental truths about stellar structure and evolution, and she devoted considerable effort to classifying and understanding them. Her approach was always empirical, grounded in the careful examination of observational data rather than in theoretical speculation, and this gave her work a solidity that earned the respect of astronomers around the world. She was building, paper by paper and observation by observation, a body of work that would stand as a foundation for stellar astrophysics for decades to come, even if Harvard could not quite bring itself to acknowledge her contributions with a proper title or a reasonable salary. In 1930, she published a book titled The Stars of High Luminosity, a comprehensive treatment of the most intrinsically bright stars in the galaxy, those rare and massive objects that burn through their nuclear fuel at prodigious rates and shine with luminosities tens of thousands of times greater than that of the Sun. The book drew upon years of spectroscopic research, synthesizing observations from Harvard's extensive plate collection with theoretical insights about stellar atmospheres and energy generation, and it quickly became a standard reference in the field. Astronomers in Europe and America turned to it when they needed to understand the properties of these exceptional stars, and it cemented Cecilia Payne's reputation as one of the leading experts on stellar spectroscopy. The irony was not lost on her that she could write a book that would be consulted by professors at universities around the world while holding no professorship herself, that her words could appear in university libraries while her name could not appear in university course catalogues, but she had learned by this point to set such ironies aside and focus on the work itself. Her observational work took her regularly to Harvard's Oak Ridge Station, a facility located in the town of Harvard, Massachusetts, some 30 miles northwest of Cambridge, where the skies were darker and the seeing was better than in the increasingly light-polluted environs of the main observatory. She would travel out to Oak Ridge to make observations with the telescopes there, spending long nights in the cold dome as she guided the instruments and exposed the photographic plates that would later be analyzed back in Cambridge. There was something peaceful about those nights at the telescope, the quiet broken only by the mechanical sounds of the dome rotating and the clock drive tracking the apparent motion of the stars, and she found that she could think clearly there, her mind ranging over problems of stellar classification and spectral analysis while her hands attended to the practical business of observation. The isolation of the observatory at night was different from the isolation she felt in the institutional hierarchy of Harvard, the former a chosen solitude that nourished her work, the latter an imposed marginality that she endured because she had no other choice. She also made multiple visits during these years to European observatories, traveling back across the Atlantic to collaborate with astronomers at institutions that often proved more welcoming than her own. At observatories in England and on the continent, she found colleagues who treated her as an equal, who engaged with her ideas on their merits rather than filtering them through assumptions about what a woman could or could not contribute to science. These trips provided both professional stimulation and personal respite, a reminder that the narrow-minded policies of Harvard were not universal, that there existed places in the world where her accomplishments were recognized and celebrated. She would return from these visits refreshed, her notebooks filled with new ideas and her spirit somewhat restored, ready to resume the patient work of spectral analysis that awaited her in Cambridge. Despite holding no formal authority to do so, she began during these years to supervise graduate students, guiding them through their research projects and helping them to develop the skills they would need to become professional astronomers. Students sought her out because of her expertise, because she understood stellar spectra better than almost anyone at the observatory, and she gave generously of her time and knowledge even though she received no compensation or recognition for this teaching. She would meet with students in her office or in the plate stacks, walking them through the techniques of spectral classification and discussing the interpretation of their observations, and many of these students would go on to have distinguished careers of their own, carrying forward the methods and approaches they had learned from her. It was a kind of underground pedagogy, teaching conducted outside the official channels of the university, but it was pedagogy nonetheless, and it shaped the next generation of stellar astronomers in ways that Harvard's administration never fully appreciated. Her lectures attracted students as well, those who heard about her knowledge and sought out opportunities to learn from her even though the university refused to list her courses in its catalog. She would give talks and informal seminars, and students would attend, some of them officially enrolled in Harvard programs and some of them simply drawn by intellectual curiosity, and she would share with them her understanding of how stars work, of what their spectra reveal about their temperatures and compositions and evolutionary states. That these lectures went unrecorded in the official catalog was a small humiliation, one of many that she learned to accept as the price of remaining at an institution that valued her work while refusing to value her, but she gave the lectures anyway, because the work of teaching seemed to her as important as the work of research, and because she could not bear to turn away students who genuinely wanted to learn. The disparity between her salary and those of her male colleagues was substantial and unambiguous, a matter of simple numbers that required no interpretation. Men who had accomplished less than she had, who had published fewer papers and made smaller contributions to the field, received salaries that were multiples of her own, and this remained true throughout the 1920s and into the 1930s, year after year, as her international reputation grew and Harvard's recognition of her did not. She did not complain publicly about this inequity, because complaining would have accomplished nothing and might well have cost her the position she did have, but she was aware of it, aware that the institution was extracting from her a kind of labor subsidy, paying her less than her work was worth because it could, because she was a woman and because there was nowhere else she could go that would give her access to the resources she needed to continue her research. The Harvard plate collection was irreplaceable, the accumulated record of decades of systematic observation, and she needed it for her work, and so she stayed, and she accepted the inadequate salary, and she continued to produce research of the highest quality. There was a particular kind of loneliness to her position during these years, the loneliness of being neither faculty nor mere assistant, of occupying a space that the institution had not quite designed and did not quite know how to accommodate. She was too accomplished to be treated as a subordinate but too female to be granted the status that her accomplishments warranted, and this left her in a kind of professional limbo, respected by her peers but marginalized by her employer. She had colleagues who valued her work and students who sought her guidance, but she did not have the security of a faculty appointment or the recognition of an official title, and this absence of formal standing was a constant low-grade reminder that her place in the institution was provisional, that it could be revoked at any time if the administration decided that her services were no longer required. And yet the work continued, day after day and year after year, the patient accumulation of observations and analyses that would eventually transform our understanding of what stars are made of. She analyzed thousands of stellar spectra during this period, each one a small piece of a vast puzzle, and she began to see patterns and relationships that had not been apparent before, ways of connecting the properties of stars to their evolutionary histories and their ultimate fates. The work was its own reward, in a sense, the satisfaction of solving problems and discovering truths about the universe, and she threw herself into it with a dedication that left little room for bitterness or self-pity. There would be time later, perhaps, to reflect on the injustices she had endured, but for now there was the work, and the work was enough, or at least it had to be enough, because it was all that the institution was willing to give her. In the year 1933, Cecilia Payne traveled to Europe, as she did from time to time, to visit observatories and to attend conferences and to maintain the collegial connections that bound the international astronomical community together across oceans and continents. It was during this particular journey that she found herself in Germany, a country then in the early and increasingly troubling months of a new political regime, and it was there, in circumstances that were marked by uncertainty and displacement, that she met a man named Sergei Illarionovich Gaposchkin, a Russian-born astronomer whose path to that moment had been considerably more difficult than her own. Sergei Gaposchkin had been born in the Russian Empire, in a time before the revolutions that would reshape that vast nation, and he had trained as an astronomer and had begun what he hoped would be a career devoted to the study of the stars. But the political upheavals that swept through Russia in the early decades of the 20th century had made life increasingly impossible for many scientists and intellectuals, and Sergei had eventually fled, leaving behind his homeland and becoming, in the legal terminology of the era, a stateless person. This was a precarious condition indeed, for a stateless person belonged to no nation and could claim the protection of no government, and such individuals often found themselves stranded in foreign countries, unable to work legally, unable to travel freely, and unable to secure the documents that would allow them to build stable lives. When Cecilia met Sergei in Germany, he was in precisely this difficult situation, a refugee with training and ability and ambition but without the papers that would allow him to pursue his profession or to settle permanently anywhere. Germany itself was becoming an increasingly dangerous place for refugees and for anyone whose background or beliefs did not align with the new order, and Sergei's position was growing more untenable with each passing month. Cecilia, who understood something of what it meant to struggle against institutional barriers, recognized in Sergei both a fellow astronomer and a person in genuine need of assistance. What followed was a period of persistent and patient advocacy on Cecilia's part, conducted primarily through letters and conversations with Harlow Shapley, the director of the Harvard College Observatory. Shapley, for all his complicated qualities, had demonstrated over the years a willingness to bring talented individuals to Harvard, and Cecilia made the case to him that Sergei Gaposchkin was precisely such a person, an astronomer of real ability who could contribute meaningfully to the observatory's research programs if only he could be brought to the United States and given the opportunity to work. The process of obtaining a visa for a stateless person was neither simple nor quick, involving considerable bureaucratic navigation and the marshalling of institutional support, but Cecilia pursued the matter with the same methodical determination that she brought to her scientific work, and eventually her efforts succeeded. Sergei Gaposchkin received a visa to enter the United States, along with a position at the Harvard College Observatory, and he arrived in Cambridge with the chance to begin his professional life anew. The relationship between Cecilia and Sergei had developed alongside this practical assistance, and on the 6th of March in 1934, they were married. Cecilia was then 33 years old, established in her career though still holding only the ambiguous position of technical assistant, and Sergei was beginning the work of rebuilding his professional identity in a new country with a new language. In a decision that was somewhat unusual for the era, Cecilia chose to hyphenate her surname, becoming Cecilia Payne-Gaposchkin rather than simply taking her husband's name or retaining only her maiden name. This hyphenated form preserved her identity as Cecilia Payne, the name under which she had already published significant scientific work and built her professional reputation, while also acknowledging her marriage and her new family. It was a small but meaningful assertion of continuity, a way of carrying her past into her future without abandoning either. The marriage brought together two astronomers whose skills and temperaments proved to be complementary in ways that would shape their collaborative work for decades to come. Sergei was, by inclination and training, an observer, a person who was most comfortable with the patient, methodical work of making measurements and recording data, night after night, plate after plate. He had a gift for the sustained attention that observational astronomy requires, the willingness to repeat similar tasks thousands upon thousands of times in the service of building a comprehensive record. Cecilia, by contrast, was a synthesizer, a person whose particular genius lay in seeing patterns within large bodies of data, in drawing together observations from many sources and many years and finding within them the underlying order. She could look at a collection of measurements and perceive the structure that unified them, the physical processes that explained what the numbers revealed. Together, they embarked on a program of research focused on variable stars, those stars whose brightness changes over time in patterns that can reveal fundamental information about their physical nature. Variable stars are found throughout the galaxy, in many different types and with many different periods and amplitudes of variation, and the systematic study of these objects requires exactly the combination of skills that Sergei and Cecilia each possessed. Sergei devoted himself to the painstaking work of measuring stellar brightness on photographic plates, recording observation after observation with careful precision, while Cecilia took these accumulating measurements and analyzed them, identifying patterns of variability, classifying stars according to their behavior, and working to understand what the variations revealed about stellar structure and evolution. Over the years and decades that followed, this collaborative effort would grow into one of the most comprehensive surveys of variable stars ever undertaken, eventually encompassing more than 1.25 million individual observations. The scale of this work is worth pausing to consider, even briefly, for it represents a quantity of patient, careful measurement that is difficult to fully appreciate. Each observation required examining a photographic plate under magnification, identifying a particular star among the thousands of stellar images recorded on the plate, comparing its brightness to that of reference stars, and recording the measurement along with the date and time and other relevant information. To do this more than 1 million times, over many years, required a dedication to systematic work that is perhaps the most fundamental virtue an observational scientist can possess. The years following their marriage also brought children into their household, beginning with their son Edward, who was born in 1935, followed by their daughter Catherine in 1937, and then their son Peter in 1940. These 3 children arrived during a period when Cecilia was continuing her astronomical research at a demanding pace, and when the institutional structures that might have supported a working mother were essentially non-existent. There was no formal maternity leave at Harvard, no childcare provided by the observatory, no expectation that a woman with young children would or could continue her professional work. The burden of combining motherhood with astronomical research fell entirely upon Cecilia and Sergei themselves, along with whatever private arrangements they could manage. The family made their home on Bond Street in Cambridge, in a house that became, over time, something of an informal scientific salon. Colleagues and students and visitors would gather there for conversation and discussion, and the household atmosphere was one in which scientific ideas were a natural part of daily life. The The children grew up surrounded by astronomical talk, by discussions of stellar spectra and variable stars and the great questions of astrophysics, and this immersion in scientific discourse shaped their understanding of what adult life and adult work could look like. In later years, the children would recall a household that was filled with books and ideas, where curiosity was encouraged and where the boundary between work and home was pleasantly blurred. Yet this domestic contentment existed alongside ongoing professional struggles for both Cecilia and Sergei. Her position remained precarious and poorly compensated, and his situation was in some ways even more difficult. Sergei had arrived in the United States as a refugee, with excellent training but without the network of professional connections and the established reputation that might have smoothed his path. His English, though functional, remained imperfect, and this linguistic barrier created challenges in a profession where communication and publication were essential. He experienced frustrations in building his career, difficulties in finding the recognition and the permanent position that his abilities might have warranted, and these struggles were a source of ongoing stress for the family. The complementary nature of their working styles helped to make their collaboration productive, but it also meant that Sergei's contributions were sometimes less visible than Cecilia's. The work of synthesis and interpretation, of drawing conclusions and writing papers, tends to receive more attention than the work of gathering data, even when both are equally essential. Cecilia was the one who wrote most of their joint publications, who presented their findings at conferences, who engaged in the theoretical debates of the field, while Sergei continued the quiet, essential work of measurement and observation. This division of labor was practical and effective, but it may also have contributed to a certain imbalance in how their respective contributions were perceived by the wider astronomical community. Their family life incorporated their scientific interests in ways both large and small. Camping trips, which the family took during summers and holidays, were often combined with astronomical observation, so that the experience of being outdoors under the night sky became intertwined with the work of studying that sky systematically. The children learned to see the stars not merely as beautiful points of light but as objects of scientific interest, each one a sun with its own properties and its own story. This blending of recreation and research was characteristic of a household in which astronomy was not merely a profession but a way of engaging with the world. The years between 1934 and 1940 were thus a period of building, for Cecilia Payne-Gaposchkin, in multiple senses of that word. She was building a family, with all the daily demands and deeper satisfactions that family life entails. She was building a collaborative research program with her husband, one that would eventually produce an extraordinary record of systematic observation. She was building a home that served as a gathering place for scientific conversation and intellectual community. And she was continuing to build her own career, publication by publication, observation by observation, even as the institutional recognition that her work deserved remained frustratingly out of reach. The challenges she faced during this period were substantial, and they were challenges that few of her male colleagues would have encountered in the same form. The expectation that she would manage household and children while maintaining her research output, the lack of any institutional support for doing so, the continued ambiguity of her professional status, and the additional complexity of supporting her husband through his own professional difficulties, all of these burdens fell upon her during years when she was also in the most productive phase of her scientific work. That she managed to carry these burdens while continuing to contribute significantly to astronomical knowledge is a testament to her remarkable capacity for sustained effort and her deep commitment to her science. The household on Bond Street, filled with children and visitors and astronomical discussion, represented a kind of life that Cecilia had perhaps not imagined for herself during her student years in Cambridge, England, when she had been a young woman passionately devoted to science and uncertain whether marriage and family would ever be part of her future. That she found both, and that she found them in combination with continued scientific productivity, was a source of genuine happiness, even amid the frustrations and difficulties that accompanied her professional situation. The years of building a family were also years of building knowledge, and both forms of building would continue, steadily and patiently, in the decades that followed. In the years following 1940, Cecilia Payne-Gaposchkin turned her attention toward a vast and patient undertaking, one that would occupy her thoughts and her working hours for more than 15 years, and one that required the sort of sustained dedication that comes more easily to those who find genuine contentment in the slow accumulation of knowledge rather than in sudden moments of revelation. The project concerned variable stars, those distant suns whose brightness rises and falls in patterns that can be measured and studied and, with enough care and enough time, understood. She was not alone in this work, for her husband Sergei worked alongside her, the two of them settling into a rhythm of shared labor that would come to define this middle portion of her scientific life, and together they embarked upon what can only be described as a monumental campaign of observation and cataloging, focused particularly upon the variable stars found within the Magellanic Clouds. The Magellanic Clouds, for those who may be encountering the term for the first time or who have perhaps forgotten from some long ago reading, are two small irregular galaxies that accompany our own Milky Way through the cosmos, visible from the southern hemisphere as faint patches of light that ancient peoples noticed and wondered about, and that modern astronomers have studied with increasing precision and care. Within these satellite galaxies lie thousands upon thousands of stars, and among those stars are many whose brightness does not remain constant but instead varies over time, sometimes in regular cycles that repeat with clockwork precision, and sometimes in more irregular patterns that require longer observation to discern. Cecilia understood that these variable stars held within their changing light important clues about the nature of stellar evolution, about the distances between galaxies, and about the structure of the universe itself, and so she committed herself to their systematic study with the same thoroughness that had characterized her earlier work on stellar atmospheres and chemical abundances. The raw material for this research came from the Harvard Plate Collection, that extraordinary archive of photographic observations that had been accumulating at the observatory for decades, each glass plate preserving a record of the sky as it appeared on a particular night from a particular location, the stars captured as tiny points of varying darkness against the lighter background of the exposed emulsion. These plates were stored in careful sequence, catalogued and preserved, and they represented an almost incomprehensibly rich resource for anyone willing to undertake the painstaking work of comparing images taken at different times, noting which stars had grown brighter or dimmer, measuring those changes with precision, and recording the results in forms that could be analyzed and understood. Cecilia and Sergei did exactly this, hour after hour and year after year, examining plates that spanned not merely months but decades of observation, building up a picture of stellar variability that grew more detailed and more comprehensive with each passing season. The technique they employed, photographic photometry, involved measuring the brightness of stars as recorded on these glass plates, comparing the size and darkness of stellar images to determine relative magnitudes, and tracking how those magnitudes changed from one observation to the next. It was a method that Cecilia championed throughout her career, recognizing both its power and its limitations, understanding that while it lacked the precision of more modern electronic techniques that would later emerge, it offered something invaluable in the form of historical depth, for the plate collection contained observations stretching back to the 1880s, providing a baseline of data that no newly invented instrument could possibly match. She was committed to extracting every possible fragment of scientific value from this archive, treating the old plates not as obsolete relics but as precious records of celestial events that could never be observed again except through the preservation of their photographic traces. The identification and cataloguing of variable stars in the Magellanic Clouds was not glamorous work in the way that some astronomical discoveries capture the public imagination, but it was essential work nonetheless, the sort of careful foundation laying that makes later advances possible. Cecilia and Sergei identified thousands of variable stars during these years, sorting them into categories based on the nature of their variability, measuring their periods and amplitudes, constructing light curves that showed how their brightness changed over time, and gradually building up a comprehensive understanding of the variable star populations within these nearby galaxies. The work required patience above all else, and a willingness to proceed methodically even when progress seemed slow, and a faith that the accumulation of individual observations would eventually yield insights of genuine importance. Among the variable stars that commanded particular attention were the Cepheid variables, a class of pulsating stars whose importance to astronomy can scarcely be overstated. Cepheids vary in brightness not because of eclipses or surface spots but because they physically pulsate, expanding and contracting in regular cycles that cause their luminosity to rise and fall in predictable patterns. What makes them so valuable is the relationship between their pulsation periods and their intrinsic brightness, a correlation first discovered by Henrietta Leavitt working at Harvard decades earlier, which allows astronomers to use Cepheids as standard candles for measuring cosmic distances. If you can observe a Cepheid, measure its period of variation, and compare its apparent brightness to the intrinsic brightness implied by that period, you can calculate how far away it must be, and this technique has proved essential for establishing the scale of the universe. Cecilia's careful studies of Cepheids in the Magellanic Clouds contributed to the refinement of these distance measurements, helping to calibrate the cosmic distance ladder with greater precision and thereby improving our understanding of how far away these satellite galaxies actually lie. She also devoted considerable attention to novae, those dramatic stellar explosions in which a previously inconspicuous star suddenly flares to enormous brightness before gradually fading back toward obscurity. The light curves of novae, showing how their brightness changes in the days and weeks and months following their eruption, contain information about the physical processes underlying these cataclysmic events, and Cecilia studied them carefully, measuring their rise times and decline rates, noting the differences between fast novae and slow novae, and working to understand what these variations might reveal about the stars themselves and the circumstances of their explosions. The old Harvard plates were particularly valuable for nova research, since they often contained serendipitous records of nova outbursts that had occurred years or decades earlier, waiting to be discovered by someone with the patience and the expertise to recognize them. Throughout this period of intensive variable star research, Cecilia continued her spectroscopic work as well, studying the spectra of stars to learn about their temperatures and chemical compositions and the physical conditions in their atmospheres. She was particularly interested in questions of stellar populations, the way that different types of stars cluster together in different regions of a galaxy, and what these population differences might reveal about the history and evolution of stellar systems. The spectroscopic techniques she had mastered during her thesis work remained central to her research program, complemented now by the photometric methods that allowed her to track how stellar properties changed over time. The Second World War brought disruptions to astronomical research as it did to so many other aspects of life, and during these years Cecilia contributed to military-related scientific work, applying her technical skills and her methodical approach to problems of more immediate practical concern. The details of such wartime contributions were often kept quiet, as was customary during that era, but like many scientists of her generation, she found herself drawn into the broader national effort, putting aside purely astronomical questions for a time in service of more pressing needs. When the war ended and normal scientific life gradually resumed, she returned to her variable star campaign with renewed dedication, the years of interruption having done nothing to diminish her commitment to the long-term project she had set for herself. In 1954, Cecilia published a book titled Variable Stars and Galactic Structure, which synthesized more than a decade of her research on variable stars and placed it within the broader context of galactic astronomy. The book represented a substantial achievement, gathering together the results of countless observations and measurements, presenting them in organized form, and drawing out the implications for our understanding of how galaxies are structured and how they evolve. It was the sort of comprehensive treatment that only someone who had lived with the data for many years could produce, reflecting not merely technical competence but genuine familiarity with the subject in all its complexity and detail. During these same years, Cecilia's frustration with the institutional barriers she faced at Harvard found occasional expression, though she was not by nature inclined toward complaint or confrontation. She reportedly observed that her position at the university was indeterminate, a wry characterization that captured something of the ambiguity she had endured for so long, doing work of genuine distinction while holding titles that did not reflect her actual contributions or her standing in the scientific community. She had been at Harvard for decades by this point, had trained students and published papers and built a reputation that extended far beyond Cambridge, and yet the formal recognition that would have been routine for a male scientist of comparable achievement remained frustratingly out of reach. Her expertise, however, was undeniable, and she found herself increasingly called upon to serve in leadership roles within the astronomical community, even as Harvard itself remained slow to acknowledge her properly. She was elected to positions of responsibility within the American Astronomical Society, the professional organization that brought together astronomers from across the country, and she served in these roles with the same conscientiousness that characterized her research. Her attendance at astronomical conferences became a regular feature of the scientific calendar, and at these gatherings her contributions to discussions and her presentations of new results commanded respect and attention from colleagues who judged her work on its merits regardless of what title she held at her home institution. Her lectures and public speaking engagements also increased during this period, as she became more widely known not only among professional astronomers but among broader audiences interested in the wonders of the night sky. She had a gift for clear explanation, for presenting complex ideas in terms that non-specialists could follow, and she found genuine satisfaction in sharing her enthusiasm for stellar astronomy with students and general audiences alike. The act of teaching, of guiding younger minds toward understanding, was something she valued deeply, and she mentored a generation of astronomers during these years, both male and female, passing along not only technical knowledge but also something of her approach to scientific work, her patience and thoroughness, and her commitment to following the evidence wherever it might lead. The students who worked with her learned by example what it meant to do careful observational science, to build understanding through the accumulation of individual measurements, to resist the temptation of premature conclusions, and to maintain standards of precision and honesty even when the work was tedious or the results were ambiguous. She was not a dramatic teacher given to theatrical flourishes, but rather a steady and reliable guide who demonstrated through her own practice what good scientific work looked like. The astronomers she trained went on to their own careers and their own contributions, carrying with them something of what they had learned in her company, and in this way her influence extended well beyond her own publications and her own discoveries. The variable star campaign that occupied these 16 years from 1940 to 1956 represented in many ways the consolidation of Cecilia's position as one of the leading observational astronomers of her generation. The work was not revolutionary in the way her thesis had been, challenging established ideas and forcing the scientific community to reconsider fundamental assumptions, but it was valuable and substantial and enduring, the kind of careful empirical contribution upon which the progress of science ultimately depends. She had found her rhythm as a scientist, working steadily and productively year after year, and if the external recognition she deserved remained incomplete, she had at least the satisfaction of knowing that her work was good and that it would stand the test of time. In the year 1956, something quietly remarkable occurred in the administrative offices of Harvard University, though you would have been forgiven for missing it entirely if you had not been paying close attention to the careful movements of academic bureaucracy. After 31 years of working at the institution, after 3 decades of teaching and researching and publishing and contributing to the fundamental understanding of what stars are made of, Cecilia Payne-Gaposchkin received a letter informing her that she had been promoted to the rank of full professor through the Faculty of Arts and Sciences. This was not merely a personal achievement, though it was certainly that, but rather a small crack in a very old wall, for she had become the first woman ever to reach this rank through that particular faculty in all of Harvard's long history. The wall had stood for more than 300 years, and now, in the autumn of her career, she had been permitted to step through a door that had never before been opened to someone of her sex. You might imagine that such a moment would call for celebration, for champagne perhaps, or at the very least for some expression of triumph after so many years of being passed over and undervalued and paid less than her male colleagues for performing the same work and often more of it. But those who knew Cecilia understood that her response was characteristically muted, almost subdued, as though the recognition had arrived too late for her to receive it with the uncomplicated joy it might once have inspired. She had waited too long, you see, and something in the waiting had changed the shape of what the achievement meant to her. It was rather like being handed a glass of water after you have already walked through the desert and reached the other side on your own, parched and exhausted but somehow still standing. You accept the water, certainly, and you are grateful in your way, but the desperate thirst that would have made it taste sweet has already passed into memory. In the same year, Harvard bestowed upon her another distinction that had likewise never been granted to a woman within its walls. She was appointed chair of the astronomy department, a position she would hold from 1956 until 1960, and this too was a first, another small door opening in that ancient wall. The department she now led was the same one where she had arrived as a young graduate student from England more than 3 decades earlier, filled with questions about the composition of stellar atmospheres and armed with the mathematical tools to pursue answers that would ultimately reshape our understanding of the universe. Now she sat in the chair's office, responsible for the administration and direction of the very program that had once barely known what to do with a woman of her talents and ambitions. Her title was expanded and elevated in ways that reflected the esteem her colleagues had come to hold for her, even if that esteem had been rather slow in translating itself into formal recognition. She was designated the Phillips Astronomer of Harvard, a title that carried with it both honor and the acknowledgement that her contributions to the field had been substantial and enduring. The title suited her, fitting comfortably alongside the other designations she had accumulated over the years, each one a small marker of the distance she had traveled from the young woman who had first looked through a telescope in Cambridge, England, and felt the universe open up before her like a book written in a language she was determined to learn. Those who attended her lectures during these years would later speak of them with a particular kind of reverence, the sort reserved for experiences that shaped the course of a life. Her teaching style was demanding, certainly, and she expected much from her students, perhaps because so much had always been expected of her and she had learned to meet those expectations through sheer determination and countless hours of careful work. But alongside that demanding quality there existed something else, something that her students described as inspiring, though that word perhaps fails to capture the full texture of what it felt like to sit in her classroom and listen to her speak about the stars. She delivered her lectures without notes, which was remarkable given the complexity of the material she covered and the precision with which she covered it. The information seemed to flow from her as naturally as water flows downhill, each fact connected to the next by invisible threads of understanding that she had spent a lifetime weaving together. She would stand before her students and speak of stellar classification and spectral analysis and the chemical abundances of distant suns, and the words came out in complete sentences that seemed to have been crafted in advance, though in truth they were being assembled in the moment from the vast storehouse of knowledge she carried within her. Her students watched and listened and took notes, and many of them found themselves changed by the experience, their own ambitions kindled by the example of this woman who had pursued understanding with such single-minded devotion. The recognition that came to her during these years was not limited to Harvard alone, though Harvard's recognition carried a particular weight given how long it had been withheld. Earlier in her career, in 1934, she had received the Annie Jump Cannon Award, which was given to women astronomers in recognition of distinguished contributions to the field. The award was named for another pioneering woman astronomer who had worked at Harvard, and there was a certain poetry in Cecilia receiving an honor that bore the name of someone who had helped pave the way for women in the observatory, even if the path remained far narrower and more difficult than it should have been. In 1952, Radcliffe College had granted her its Award of Merit, acknowledging the significance of her work and her connection to the institution where she had technically earned her doctorate all those years ago, since Harvard itself had not yet begun granting degrees to women when she completed her research. These awards accumulated like small stones in a can, each one marking a point on her journey, and while no single stone could fully represent the magnitude of what she had accomplished, together they formed something that approximated recognition. The honorary degrees began to arrive as well, conferred by institutions that wished to associate themselves with her name and her achievements. Wilson College granted her one, as did Smith College and Western College and Colgate University, each ceremony requiring her to don academic robes and sit through speeches and accept scrolls and handshakes from administrators who spoke of her contributions to human knowledge. In 1967, Cambridge University, the institution where she had first studied and where she had been denied a degree simply because of her sex, finally granted her an honorary doctorate, and this particular recognition must have carried a complicated weight, arriving as it did from the place that had both nurtured her early passion for astronomy and simultaneously refused to acknowledge that passion with the credential it deserved. Her election to the American Academy of Arts and Sciences represented another form of recognition, an acknowledgement by her peers that she had earned a place among the most distinguished scholars and scientists of her generation. The Academy had been founded in 1780 by John Adams and other figures from the early days of the American Republic, and its membership rolls read like a catalogue of intellectual achievement across nearly 2 centuries. Now her name was added to those rolls, another marker of the distance she had travelled and the contributions she had made. During these years, she continued to write and to publish, for the work of understanding the universe was never truly finished, and there were always more questions to pursue and more data to analyze. In 1954, she published a textbook titled Introduction to Astronomy, which distilled her decades of knowledge and teaching experience into a form that students could use to begin their own journeys into the field. The book reflected her characteristic thoroughness and her gift for explaining complex concepts in language that was precise without being impenetrable, and it served as a guide for countless young people who were just beginning to look up at the night sky and wonder what the stars were made of. 3 years later, in 1957, she published The Galactic Novae, a more specialized work that focused on a particular type of stellar phenomenon that had long fascinated her. Novae are stars that suddenly increase dramatically in brightness before fading again over weeks or months, and understanding them required precisely the sort of careful spectroscopic analysis that Cecilia had spent her career perfecting. The book represented the accumulated wisdom of years of observation and analysis, each page dense with the kind of detailed information that could only come from someone who had spent countless hours peering at photographic plates and measuring spectral lines and thinking deeply about what the light from distant stars could tell us about the processes unfolding within them. She supervised numerous doctoral students during these years, guiding the next generation of astronomers through the challenges and rewards of original research. Many of these students went on to become prominent astronomers in their own right, carrying forward the methods and approaches they had learned under her supervision. She was demanding of them, as she had always been demanding of herself, but that demanding quality was tempered by genuine investment in their success and by the generosity with which she shared her knowledge and experience. To be her student was to be held to high standards, but it was also to be given the tools and the encouragement necessary to meet those standards. Her office in the Harvard Observatory became something of a pilgrimage site for young women who were considering careers in science and who needed to see, in concrete and living form, that such careers were possible despite all the obstacles that society placed in their path. They would make their way to her door and knock, and she would invite them in and speak with them about the work and about the challenges and about the peculiar satisfaction that came from adding some small piece to the vast puzzle of understanding the universe. She did not sugarcoat the difficulties, for she had experienced too many of them herself to pretend they did not exist, but neither did she discourage, for she understood that the presence of a single example, a single woman who had managed to break through the barriers and establish herself as a respected scientist, could make all the difference to someone who was wondering whether the struggle was worth undertaking. The years between 1956 and 1966 were thus a time of recognition and of consolidation, a period when the professional respect she had long deserved finally began to be expressed in the formal structures of academic life. The barriers had not fallen entirely, of course, and there was still much work to be done before women would be able to pursue scientific careers on anything like equal footing with their male colleagues. But the doors she had opened would remain open for those who came after her, and the path she had walked, difficult as it had been, was now at least visible to others who might wish to follow it. She continued to work, as she had always worked, rising early and making her way to the observatory and spending her hours in the patient analysis of data and the careful construction of understanding. The stars she studied were impossibly distant, their light having traveled for years or decades or centuries before reaching the instruments that gathered it, but through that light she could read the stories of their composition and their temperature and their motion and their fate. It was quiet work, methodical work, the sort of work that required patience and attention and a willingness to spend years pursuing answers to questions that might seem esoteric to those outside the field. But she had never minded the quietness or the patience, for she had understood from the beginning that understanding the universe was not the work of a moment but the work of a lifetime, and she had given her lifetime to it without reservation or regret. In 1966, Cecilia Payne-Gaposchkin reached the age of 66, and according to the policies then in place at Harvard University, this meant that her formal employment would come to an end, as mandatory retirement was simply the way of things in those days, a threshold that arrived regardless of whether one's mind remained sharp or one's curiosity still burned with the steady flame it had always possessed. She had spent more than 4 decades at this institution, first as a graduate student who had arrived from England with her remarkable thesis already taking shape in her thoughts, then as a technical assistant whose title had so poorly reflected the scope of her contributions, and finally, in her later years, as the first woman to hold a full professorship in Harvard's Faculty of Arts and Sciences and the first woman to chair a department there. All of this had happened within these grounds, among these buildings and telescopes and libraries, and now the calendar had simply declared that her time of formal service had concluded. But of course, as anyone who knew her would have expected, retirement in Cecilia's case was something of a technicality, a change in her official status that did not particularly correspond to any change in her daily activities or her commitment to understanding the stars. Harvard granted her the title of Professor Emerita, which is the designation given to retired faculty members who have distinguished themselves in their fields and who remain connected to their institutions in an honorary capacity, and along with this title came the continuation of certain privileges, including the maintenance of an office where she could carry on with her research and her correspondence and her reading. This office became her anchor, the place where she would arrive each day to examine new data, to consider problems that still interested her, to exchange letters with colleagues around the world who continued to seek her expertise on matters of stellar classification and composition. The transition from active professor to emerita professor seems to have been, for Cecilia, more a matter of paperwork than of any fundamental shift in how she spent her hours. She had always been someone who worked because the work itself compelled her, not because a schedule or a salary demanded it, and so she simply continued working, as one might continue breathing or thinking, because it was simply what she did. During these years following her formal retirement, Cecilia undertook a project of a more personal nature, though one that would prove valuable to historians of science and to anyone interested in understanding the landscape of 20th century astronomy through the eyes of someone who had helped to shape it. She began dictating her autobiography, and the person who received these dictations and helped to organize them into a coherent narrative was her daughter Catherine, who served as both audience and collaborator in this intimate process of remembering. The resulting work was published in 1968 under the title An Autobiography and Other Recollections, and in its pages Cecilia reflected on her childhood in England, on the moment when she had heard Arthur Eddington lecture on his eclipse expedition and had felt the course of her life shift irrevocably, on her years of struggle and accomplishment at Harvard, on the satisfaction of her marriage to Sergei, and on the countless individual discoveries and disappointments and quiet triumphs that had accumulated across her decades of study. The act of dictation suited her well, as she had always possessed a facility with spoken language that matched her precision with written prose, and Catherine's presence allowed the process to feel less like a formal composition and more like a conversation, a sharing of memories between mother and daughter that happened to be preserved for others to read. Throughout the late 1960s and into the 1970s, Cecilia continued to publish, though the nature of her publications shifted somewhat as she moved further into her emerita years. While she still contributed to technical astronomical literature when new observations or analyses warranted it, she increasingly turned her attention to popular science writing, to the composition of articles and essays that would make the wonders of stellar astrophysics accessible to readers who did not possess advanced training in the field. This was not a diminishment of her work, but rather an expansion of it, a recognition that the knowledge she had spent her life accumulating could be shared more broadly, could reach students who might one day become astronomers themselves, could reach curious adults who simply wished to understand what the stars were made of and how we had come to know such things. She wrote with the same clarity and care that had characterized her scientific papers, but she allowed herself a certain warmth, a willingness to convey not just the facts but the beauty that had drawn her to astronomy in the first place. In 1976, a decade after her formal retirement and more than half a century after she had arrived in America as a young woman with her Cambridge education and her determination to study the stars, Cecilia Payne-Gaposchkin received the Henry Norris Russell Prize from the American Astronomical Society. This award is the highest honor that the Society bestows, given annually to an astronomer in recognition of a lifetime of distinguished contributions to the field, and it takes its name from Henry Norris Russell himself, the Princeton astronomer who had once convinced the young Cecilia to soften the conclusions of her doctoral thesis, the man who had later acknowledged her primacy in determining stellar composition. There is a certain layered quality to this honor, the way it connected Cecilia back to those early years when Russell's skepticism had caused her to step back from her own correct conclusions, and the way it now placed her at the very pinnacle of astronomical achievement, her name inscribed among the most accomplished practitioners of the discipline she had loved since childhood. She was the first woman ever to receive this prize, a distinction that reflected both her individual excellence and the broader truth that women in astronomy had faced obstacles that made such recognition rare, and she accepted it with the characteristic blend of graciousness and clear-eyed honesty that had always marked her public appearances. The years of her emerita status were also years of travel, as invitations arrived from institutions around the world, and Cecilia accepted many of them, journeying to places she had perhaps not expected to visit in her earlier years when the demands of research and teaching had kept her close to Cambridge. She traveled to Japan, where astronomical research was flourishing and where colleagues were eager to hear her speak about her work and her experiences. She traveled to various countries in Europe, returning to the continent of her birth to lecture at universities and observatories that valued her perspective and her accomplishments. These journeys must have offered her a different vantage point on her own career, allowing her to see how her contributions had been received and built upon by researchers working in different contexts and traditions, how the knowledge she had helped to establish about stellar composition had become foundational to astrophysics everywhere that astrophysics was practiced. As Cecilia grew older and as she spoke more frequently about the history of her field and her own place within it, her reflections on the discrimination she had faced as a woman became increasingly outspoken. In her younger years, she had sometimes been reluctant to dwell on these matters, preferring to let her work speak for itself and perhaps believing that complaint was unlikely to change entrenched attitudes. But with the authority that came from her age and her achievements and her formal recognition by her peers, she began to speak more directly about what she had experienced and what women in science continued to experience. She described the years of inadequate titles and insufficient pay, the assumption that a woman could not be a professor, the way her contributions had sometimes been overlooked or attributed to others. These reflections were not bitter, precisely, but they were honest, and they served to illuminate for younger generations of scientists the obstacles that had been placed in the paths of women who wished to study the stars. Among the remarks that Cecilia made during these later years, one has been remembered and repeated with particular frequency, a piece of advice that she offered to those who might be considering a scientific career. She said that one should not undertake a scientific career in quest of fame or money, because there are easier and better ways to reach them. This observation contained within it a lifetime of experience, a recognition that science demanded sacrifices that only passion for the work itself could justify, and a gentle suggestion that those who pursued science for external rewards were likely to find themselves disappointed, while those who pursued it for the intrinsic satisfaction of understanding the universe were likely to find themselves fulfilled regardless of whether recognition or remuneration ever arrived. It was practical advice, born of practical experience, and it conveyed something essential about Cecilia's own motivations, the way she had continued her research not because it brought her status or wealth, but because the stars themselves compelled her attention. Throughout her emerita years, Cecilia continued to collaborate with Sergei, her husband, who shared her devotion to astronomy and who remained her closest intellectual companion. They had worked together for so many years by this point, examining variable stars and analyzing spectroscopic data and publishing their findings jointly, that their professional partnership had become as natural as their domestic one. This collaboration would continue until Sergei's death in 1984, which occurred after Cecilia's own passing, but during the years we are considering now, the late 1960s through the 1970s, they worked side by side as they always had, two aging astronomers who still found the universe endlessly interesting. As Cecilia moved through her 70s, certain aspects of her personality and presentation became increasingly pronounced, and those who encountered her during these years often came away with vivid impressions that they would later share in their own reminiscences. She had always possessed a distinctive sense of personal style, and in her later years this became even more marked, with clothing choices that were entirely her own, that reflected no particular fashion but rather her own preferences and perhaps a certain indifference to conventional expectations about how a woman of her age and station should appear. She was known for her consumption of strong tea, prepared in quantities and concentrations that others found remarkable, and for her habit of chain smoking, which was common enough among her generation but which added to the overall impression of someone who lived according to her own inclinations rather than according to guidelines about health or propriety. These eccentricities became legendary among those who knew her or knew of her, small details that humanized the great scientist and made her seem approachable even as her intellectual achievements placed her in rarefied company. The mentorship that Cecilia had provided to younger astronomers throughout her career continued during these years, though in a more informal capacity now that she no longer held an official position in the department. Students and postdoctoral researchers still sought her out, still valued her opinions on their work and her advice on their careers, and she gave of her time and her knowledge generously, as she always had. She had trained so many astronomers over the decades, had guided so many through their dissertations and their early papers, and now she continued to support the next generation simply because supporting the next generation was something she believed in, something that gave her satisfaction. Those who interacted with Cecilia during her 70s often remarked on the extraordinary persistence of her mental faculties, and in particular on her memory, which remained photographic well into these later years. She could recall details of observations made decades earlier, could cite specific measurements and dates and page numbers from papers published long ago, could summon from her vast store of knowledge precisely the information that a conversation required. This ability had served her well throughout her career, allowing her to hold in her mind the complex web of data and theory that constituted stellar astrophysics, and it continued to serve her now, making her a living repository of astronomical history and a resource of extraordinary value to anyone studying the development of the field. And so the years passed, each one bringing its own small accumulations of work and memory, its own lectures and publications and conversations, its own quiet satisfactions. Cecilia Payne-Gaposchkin had entered her retirement as one of the most honored astronomers in the world, and she continued to inhabit that role with grace and dedication, contributing what she could, sharing what she knew, and looking up at the stars with the same wonder that had filled her since she was a girl in Wendover, in England, in a time that now seemed very distant indeed, but that remained vivid in her photographic memory. A beginning that had led to all of this, to a life spent understanding what the stars were made of and how they came to be. On the 7th of December, in the year 1979, in the city of Cambridge, Massachusetts, where she had spent the greater part of her professional life, Cecilia Payne-Gaposchkin died quietly from lung cancer at the age of 79. The winter light that day was pale and brief, as December light tends to be in New England, and the woman who had spent her life studying the light of distant stars was no longer among the living. She had been unwell for some time, as these things often go, and her passing, though mourned deeply by those who knew her and by the broader scientific community that had come to recognize her contributions, was not unexpected. She died in the same city where she had arrived as a young woman more than 50 years earlier, full of questions about the composition of stars, and where she had eventually found answers that would reshape our understanding of the universe itself. Her funeral services were held in Cambridge, attended by colleagues, students, former collaborators, and of course her family, who had walked alongside her through decades of research and teaching and the quiet daily work of a life devoted to science. She was buried in the Mount Auburn Cemetery, that peaceful and historic resting place in Cambridge where many notable figures of American intellectual life have been laid to rest, beneath trees that change with the seasons and along pathways that wind gently among the graves. It is a tranquil place, well suited to someone who spent her nights gazing at the slow and patient movements of celestial bodies, and her days carefully recording their properties with the same unhurried dedication. The grave marker, simple and dignified, notes her name and her years, and those who visit can stand there in the quiet and reflect on all that she accomplished during her time on this particular planet, orbiting this particular star, whose composition she was among the first to truly understand. In the weeks and months following her death, obituaries appeared in major scientific journals, each one attempting to summarize a life of remarkable achievement. The publications of record in the fields of astronomy and astrophysics noted that she had fundamentally transformed our understanding of stellar composition, that her 1925 doctoral thesis had been described by some as the most brilliant ever written in the field, and that her subsequent decades of research had contributed immensely to our knowledge of variable stars and the structure of the Milky Way galaxy. These obituaries were written in the measured language of scientific tribute, acknowledging her contributions with the kind of careful precision that she herself would have appreciated. They noted her pioneering status as the first woman to earn a doctorate in astronomy from Radcliffe College, her long struggle for recognition at Harvard, her eventual appointment as the first female full professor in the Faculty of Arts and Sciences, and her tireless dedication to the training of future astronomers. The tone of these memorials was respectful and admiring, as befitting someone who had done so much to advance human knowledge of the cosmos. In the years that followed, various efforts were made to honor her memory and to ensure that her contributions would not be forgotten. Harvard University, where she had spent her entire American career, established the Payne-Gaposchkin Fellowship, a recognition designed to support promising researchers in the field she had done so much to advance. This fellowship, bearing her name, has since helped numerous young scientists pursue their own investigations into the nature of stars, carrying forward the tradition of inquiry that she embodied throughout her life. It is a fitting tribute, quiet and practical, providing material support for the kind of careful research that she valued above all else. The fellowship continues to this day, a living memorial that produces tangible results in the form of new discoveries and trained scientists who go on to make their own contributions to the field. The minor planet designated 2039 was named Payne-Gaposchkin in her honor, adding her name to the celestial catalogue in a particularly appropriate way. This asteroid, a small rocky body orbiting the Sun in the vast spaces between Mars and Jupiter, now bears the name of someone who spent her life studying the composition of far larger celestial objects. There is something quietly pleasing about this tribute, the idea that a piece of the solar system itself has been labeled with her name, drifting through the darkness on its slow and predictable orbit, a permanent marker in the cosmic geography that she helped to map. Asteroids are named by the International Astronomical Union, and the decision to bestow her name upon this particular one was a recognition from the global astronomical community of her enduring importance to the field. Her personal and professional papers were carefully preserved and deposited in the Harvard University archives, where they remain accessible to researchers and historians who wish to understand her work and her life in greater detail. These archives contain her correspondence, her research notes, her unpublished writings, and various other documents that illuminate the day-to-day reality of her scientific career. For those who study the history of astronomy, or the history of women in science, or simply the intellectual development of our understanding of stellar composition, these archives represent an invaluable resource. The papers sit in their archival boxes, properly catalogued and maintained, waiting patiently for scholars who wish to examine them, much as Cecilia herself waited patiently for the recognition that she deserved but was so long denied. The recognition of her contributions continued to grow in the decades following her death, as often happens with figures whose importance was not fully appreciated during their lifetimes. Buildings were named in her honor, including the Cecilia Payne-Gaposchkin House at the Harvard-Smithsonian Center for Astrophysics, where astronomers continue the work of studying stars and galaxies and the vast structures of the universe. To have a building bear one's name is a particular kind of memorial, a daily reminder to everyone who enters that this place of research and learning is connected to a specific person who made specific contributions to human knowledge. The astronomers who work in that building, going about their daily tasks of observation and analysis and calculation, do so under the aegis of her name, whether they consciously think of it or not. In the year 2020, on what would have been her 120th birthday, the technology company Google commemorated Cecilia Payne-Gaposchkin with one of their illustrated homepage tributes, known colloquially as Google Doodles. For that day, visitors to the Google search engine were greeted with an artistic representation honoring her life and work, introducing her story to millions of people around the world who might never have encountered her name otherwise. This form of recognition, ephemeral in one sense but reaching an enormous audience, represented a kind of popular acknowledgement that would have been unimaginable during her lifetime. The doodle was seen by people in many countries, in many languages, and for at least that one day, Cecilia Payne-Gaposchkin was brought to the attention of the general public in a way that scientific obituaries and academic fellowships cannot achieve. Her influence on modern stellar composition studies is difficult to overstate, though we may attempt to describe it in measured terms. Every astronomy textbook used in universities and schools around the world teaches that stars are composed primarily of hydrogen and helium, and this fundamental fact, now so basic that it forms the foundation upon which all other stellar astrophysics is built, was her discovery. When students learn about the Sun, They learn that it is roughly 74% hydrogen by mass and roughly 24% helium, with only trace amounts of heavier elements. This information, presented as established fact in countless classrooms, was once a radical hypothesis that contradicted the prevailing scientific consensus, and it required a young woman of extraordinary intellect and determination to demonstrate its truth. Every subsequent discovery about stellar evolution, stellar nucleosynthesis, and the life cycles of stars depends upon this foundational understanding of what stars are actually made of. Biographies and popular science books have, in recent decades, revived public interest in her story and brought her achievements to the attention of readers outside the specialized world of professional astronomy. Writers and historians have examined her life with care, documenting her struggles and her triumphs, her methodical approach to research, and her quiet persistence in the face of institutional barriers. These books have found audiences among general readers who appreciate stories of scientific discovery, and among those particularly interested in the history of women in fields that were long dominated by men. Through these publications, Cecilia Payne-Gaposchkin has become better known to the public than she ever was during her lifetime, her name now appearing in lists of important women scientists and in discussions of overlooked figures in the history of astronomy. Her children, who grew up in a household filled with astronomical discussions and who witnessed firsthand their mother's dedication to her work, have continued to advocate for her recognition in the years since her death. They have participated in commemorative events, provided interviews and personal recollections to biographers and journalists, and helped to keep her memory alive through their own efforts. The family's advocacy has been an important part of the gradual process by which her contributions have come to be more widely known and appreciated. There is something touching about this continuation of her legacy through the people who knew her best, who saw her not only as a pioneering scientist but also as a mother and a family member, and who have worked to ensure that the world remembers her properly. Her story has also been claimed, and rightfully so, as part of the broader feminist reclamation of women whose contributions to science were overlooked or actively suppressed during their lifetimes. Scholars of gender and science have examined her career as emblematic of the barriers faced by women in academic settings, the ways in which credit for discoveries was sometimes attributed to men, and the institutional structures that prevented talented women from advancing in their fields. Her experience at Harvard, where she worked for years without proper title or salary commensurate with her achievements, has become a case study in the systemic discrimination that women scientists faced throughout much of the 20th century. This aspect of her legacy, while painful to contemplate, serves an important purpose in reminding us of the obstacles that had to be overcome and the work that remains to be done in creating equitable opportunities in scientific fields. Throughout her career, Cecilia Payne-Gaposchkin produced an extraordinary body of scientific work, with her publications exceeding 350 papers and books. This volume of output, sustained over more than 5 decades, represents a lifetime of dedicated research into the nature of stars and the structure of the galaxy. Each of these publications, from her groundbreaking doctoral thesis to her later works on variable stars, contributed incrementally to the vast collective enterprise of human knowledge about the universe. The papers covered topics ranging from stellar atmospheres to galactic structure to the classification of variable stars, and they were written with the same careful attention to evidence and method that characterized all of her work. Modern astronomers, when discussing the foundational figures in the field of stellar astrophysics, consistently cite Cecilia Payne-Gaposchkin as essential to the development of the discipline. Her work is not merely of historical interest, a curiosity from an earlier era of astronomy, but remains relevant and foundational to contemporary research. The techniques she developed, the questions she asked, and above all the answers she provided about the composition of stars continue to inform and guide astronomical research to this day. When astronomers point their telescopes at distant stars and analyze the light that reaches us across vast stretches of space, they do so with an understanding of stellar composition that traces directly back to her insights. And so her legacy continues, quietly and steadily, in the ongoing work of astronomers around the world, in the textbooks that teach new generations of students, in the fellowship that bears her name, in the asteroid that drifts through the solar system carrying her name with it, and in the growing recognition of her rightful place in the history of science. The light of the stars that she studied continues to travel across the universe, carrying information about their composition, and the understanding that allows us to read that information remains a gift to all who wish to comprehend the cosmos. She devoted her life to the patient work of scientific inquiry, and though she herself is no longer with us, the knowledge she generated endures, as knowledge does, passed from one generation to the next in an unbroken chain of learning and discovery.